In this presentation, I'm going to review some of the basic concepts underlying statistical inference. And this builds on and draws from ideas introduced in Lawrence Moore's SAGE textbook related to understanding significance testing. So remember that in almost all of our social science research, at least in education, we're often collecting data from a sample of cases. And the idea of making inferences is basically just answering this question. Does what we find in our sample reflect what's also happening in the population? And so the word statistic actually refers just to our calculations of sample data. And then a parameter is a numerical value that describes the characteristics of an entire population. So for example, we might have a sample mean, and then we would have a population mean. So the sample mean would be calculated with the statistic, and then we would make inferences from that to describe the population's parameter, the population mean. And so we also use different notation for our sample versus our population statistics and parameters. So a sample mean is designated, for example, by X bar. Sorry, I had to write this on here because I couldn't figure out how to get it in the keyboard, but X bar represents a sample mean, and then the population mean is represented by mu, so a Latin symbol for M, I guess. In this process of making inferences, you have to keep in mind that there's always a chance that your sample statistic might not equal your population parameter. And that's why statisticians report their results in terms of probabilities. And we'll get into this in subsequent presentations, but you'll probably, or maybe you've already heard the term p-value and t-value. So the idea is that we can never speak in terms of absolutes, like I proved my theory, because in the process of using sample data to make inferences about the population, we can never really say that we're completely right or wrong, but just that maybe we're 99.9999% chance that we are correctly estimating the population parameter from our sample statistic. And this little graphic, I know it might be hard to see, but I think it's really nice. It's from a book by Andy Field about statistics, and it really illustrates the process of taking samples from a population. And you can see here, let's say our population parameter, our mu, you'll recall that from the previous slide, is 3 for a given, measurement. That's what everybody in our population, sort of the value for that parameter is 3. Maybe it's satisfaction or something. But then if we're taking samples, maybe we take a sample of 4 people here, another sample, randomly sampling people. But as you can see, the X bar, the sample statistic for our different samples, can vary, right? Because it's not necessarily one given sample. Maybe it's representing the population and maybe it's not. So some of these X bars are 3, some are 2, 5, etc. So I think this is really nice in terms of illustrating. Maybe if we took 9 different samples, as this picture shows, you can see that while some have different means, which is called sampling variation because they have different members of the population, once we sort of pull all of those various sample means together, we can plot them out like this, right? Into a distribution. This is a nice symmetrical sampling distribution. And basically, it's a frequency distribution of all of the different sample means from our population. So this is the idea, kind of underlying idea of how we get to the population mean, right? So we can take many, many different samples, and hopefully we will be able to estimate the chances that all of these different samples are representing our population parameter. Oh, I also want to mention that this connects to that idea of standard deviation, right? So as you know, sort of standard deviation represents how close sort of the collective data points are to the mean. And so if you were to actually calculate the standard deviation between our sample means, all of these different sample means, if we calculated the standard deviation there, it would give you a measure of how much variability there is across our different samples. And that is known as the standard error of the mean. So SE, it's often represented as. And essentially, it's a measure of how representative our sample is likely to be of the population. So we're plotting that out kind of visually, and then it's also a statistic that we'll calculate and that will be reported by SPSS for us because we don't do those hand calculations really much anymore. But essentially, that's the idea of how accurate your sample means are in terms of being able to make inferences about your population mean. So a small standard error would be indicating that most sample means are similar to the population mean, and so our sample is probably likely to be accurate. But then a higher standard error means that the data is showing there's a lot of variation between the means of different samples, and so our sample probably isn't we're not as confident that our sample is as representative of our population. But again, this is this idea of using our samples to be able to make inferences about our population. Okay, so again, the key idea is that we're trying to test whether our sample statistics reflect the population parameters. In other words, what are the chances that what we found in our sample correctly captures what's going on in the population? And what are the chances that what we found in our sample is not what's going on in the population and we've made some errors? The way statisticians do this is through hypothesis testing. So you'll always have two hypotheses. First, the null hypothesis, which is designated by H0. The null is always a hypothesis that what you found is due to chance or error. So usually researchers want to be able to reject the null hypothesis. That's what we call it, reject the null hypothesis, because that means that your alternative hypothesis, which is designated by HA, often called our research hypothesis, is what we actually want to find, so that what's going on is not due to chance, but really what we're finding in our sample data is likely reflecting our population parameters. Also something I want to note is that you don't just randomly come up with an alternative hypothesis. It should be informed by prior research or theory. So this is where kind of setting up our research design and drawing from existing literature and conceptual frameworks is really important. It can help to directly inform our alternative hypothesis. Another thing to understand about hypothesis testing is that we can do one-sided hypothesis tests, which I'm going to show you an example in a second. But essentially a one-sided test tests whether or not your population parameter is higher or lower than a specific number. Or you can do a two-sided hypothesis test, which is basically whether or not your population parameter is equal to a specific number or not. So again, this is very kind of conceptual here, so I'm going to take you through a few examples of what hypothesis testing looks like. Okay, let's do some examples. We'll start with a non-directional or two-sided test. As I mentioned before, your hypothesis should be informed by the literature or prior knowledge. So let's say I knew from Government of Ethiopia reports that the average exit exam scores of high school students in Amhara was 75 in the year 2000. So I'm here in the year 2010 and I'm interested in determining whether or not the current students' scores are the same or different from the previous group. So let's say I have a sample of Amhara student exam scores, and so I need to state my hypothesis. I would do a two-sided test here because, again, I'm just interested in knowing whether or not the current score is equal to 75 or not equal to 75. So my null hypothesis, HO here, would be that the population parameter, the mean of students in 2010, is equal to 75. And my alternative hypothesis would be that it's not equal to 75. But perhaps I have some information to hypothesize that the score has gone up. Like maybe after 2000, the government implemented a new program and curriculum to improve students' test scores. And so I have reason to believe that it should be higher now in 2010. So then I would do a directional or one-sided hypothesis test. So for instance, my null hypothesis, this is important, would stay the same, HO, that my population parameter, my mean, is 75. But then my alternative hypothesis, I would say, hey, no, I have good reason to believe that the population mean should be greater than 75. So that would be how I would state my null and alternative hypothesis for this type of directional test. Okay, so my first two examples were just about a single population, right? So that is all high school students in Amhara during the year 2010. But you can also test hypotheses involving two populations. So for example, here's my last one here. Let's say I had reason to believe that in 2010, the scores of male and female students were different. So I could do a first two population non-directional test. So my two populations would be males and females. And I would state it like this, right? So my null would be that male scores are equal to that of female students' scores. And then your alternative, or my alternative hypothesis here, would be that the population mean, or the parameter of males, is not equal to that of female students. If you had reason, though, to believe that maybe males had higher scores or lower scores than females, you could change this alternative hypothesis here and make it directional the way that this one is up here. So either males greater or females greater. But again, your null is always that there is no difference between the two groups. And oftentimes our goal is to reject the null hypothesis because we want to find differences. That's what makes research interesting. Okay, so there's always the possibility of making an error when you're trying to make inferences from sample statistics to population parameters. And we're going to talk about this a lot more as we kind of go forward and get into specific tests. But I just want to introduce this idea of both type 1 and type 2 error. So type 1 is basically this idea of a false positive, or if you're rejecting the null hypothesis, but the null is actually true. So an example of this would be if you conclude that, there's a difference between male and female scores on the exit examination, when in fact, there's no difference in the population. So that's this idea of a false positive. It's usually represented by the Greek letter alpha, which again, you'll see a lot going forward as we start getting into different tests. And it's often set at like 5%, or 0.05. So again, a 5% chance that actually we're saying that there's a difference here, but we're wrong and there's really no difference. And then the opposite is type 2 error. So that's essentially a false negative. So not rejecting a null that is truly, in fact, false. So essentially it leads to the conclusion that there is no effect or difference when there is. So it'd be like if we said, oh, hey, there's no difference between males and females. This is kind of our data are leading us to conclude the, population mean of males and females is the same, but you're wrong. And so actually there's a difference between males and females. So again, it's a little bit sort of wonky to think about conceptually, but the important thing is that we're going to get to sort of these concepts in more detail as we start doing tests. And this is kind of type 1 error gets to this idea of significance level, the alpha level, which we're going to discuss more soon. And then beta, like this idea of false negatives, gets at this idea of statistical power. And so, again, these are sort of high-level concepts right now, but the important thing to remember is that there's always a possibility of making errors when we're making inferences, and that you need to be reporting and thinking about this as you're running your tests and making inferences about your population. So your conclusion should never be, I'm 100% right, I am 100% confident that I can reject the null. It's just saying that I'm pretty confident and I can give sort of an estimate of the level of error that potentially I might be wrong. Okay, so just a quick recap, this idea of hypothesis testing is central to making inferences about whether or not the data you're collecting from your sample truly represents your population. So what you do is you state a null hypothesis, an alternative hypothesis, then you select a random sample and use sampling statistics to decide whether or not to reject the null or fail to reject the null hypothesis. And so again, rejecting the null means that whatever difference you observed, either comparing your sample to a specific number, like the overall average, or comparing two samples to each other, that the difference you've observed there is large enough that it's probably not due to chance. So essentially by rejecting the null, you're accepting the alternative, and then failing to reject the null means that any of the differences that might be going on in your sample are probably just due to chance. And that is the sort of basic idea of statistical inference. And now we're going to get into actually how to apply these concepts to data and running tests.